So astronomers are like cosmic archaeologists. For example, we even define a quantity called the light year as a standard astronomical unit of distance through space, where 1 light year is the distance that light travels moving at the speed of light in 1 year's time. And it's about 9.5 trillion kilometers, or almost 6 trillion miles. And so this picture here, which is actually just an artistic rendition of our entire universe, encapsulated inside this circle here. And the way to read this is that we're located in the center at the here and now. And when we peer out into space, we're also peering back in time. And so, like, for example, here and now is here, and way out here is there and then. Okay, our solar system spans something of order, in round numbers, about 1,000 light hours ish. The contents of our Milky Way, which is this fuzzy region out here, it spans about 100,000 light years. So it takes light 100,000 years to cross from side to side. Our local group of galaxies, so the Milky Way is amongst a collection of other galaxies, including the Andromeda Galaxy and a few others that are bound together by gravity within a group. A small group, so we call it our local group of galaxies, spans roughly 10 million light years. And that's sort of this region out here, that radius away. So think of what's going on here. As we step away from the center, we're looking both out into space and back into time. Our local superclusters of galaxies are found within a region of about 1 billion light years. And then we have distant superclusters of galaxies. And you'll see that I haven't assigned a distance to it, for reasons that will become apparent later in the presentation. That's this region out here. And then this gap here, you see this dark gap. This is the epoch of the so-called dark, astronomy is labeled dark age. This is before the first stars and superstar clusters came together. And again, I've referred to it as an epoch, as opposed to some kind of distance. And finally, this boundary here is the epoch corresponding to the free flowing of cosmic radiation background left over from the Big Bang. Essentially, that was the result of the final annihilation of matter, antimatter in the early universe. All right, so we're going to talk about the expanding universe. We have to talk about spectra of galaxies, because this is how the spectra of galaxies is how we discovered the expansion of our universe. So what we have here are, so let's look at the top panel here. These are two different spectra, which is a plot of brightness of the galaxy. We have two different kinds of galaxies: a starburst galaxy and an elliptical galaxy spectrum. These are kind of two extreme examples of galaxies we find in our relatively local universe. And this is a plot of wavelength or color along the bottom axis. We have ultraviolet light over here. We have visible light between sort of this range and here. And then over here we have the infrared. So we have increasing wavelength from left to right. And see, and of course, the spectrum of a galaxy is nothing more than the composite spectrum of all the stars that make it up. It's just something all the light of the stars that make up the galaxy. And let's say up here, the universe we discovered back in the around 1930, discovered that on distance scales larger than about 10 million light years is expanding. Beyond that distance, all galaxies have motions away from us in a systematic manner. And so, and the way I think about this, the best way to think about this expansion of our universe is that its contents are becoming more and more dilute. It's a better way of thinking about it than thinking about, well, what's it expanding into? So one of the upshots is the light that arrives here and now with longer wavelengths than was emitted when it departed the galaxy. And so, well, I have to introduce here redshift. So measured wavelengths of light from a distant source of light, from, for example, a galaxy, are stretched as the universe expands with time. 1 plus this redshift factor, Z is referred to as the redshift. 1 plus that factor measures two different things that are very similar. It measures the relative size now of our universe compared to the size then. When I say now, I mean when the light that we're observing from some distant galaxy arrives here, that's now, okay? And then refers to when the light that we're observing now left that galaxy, there and then. And so over the interim time, the universe has expanded, okay? And the contents, again, think about it, have become more dilute with time. And there's a simple ratio there, which is 1 plus this redshift factor. And this also corresponds to the wavelengths of light in the, what I call the observer frame, the frame at which we're observing the spectrum, okay, in ratio to the wavelength of light emitted at rest by the galaxy then and there, okay? And so it's a ratio of those two. So here's how it works. So here's a pair of galaxies, these two extreme types, elliptical galaxy and starburst galaxy, in the local universe. So all these wavelengths, all these features that we're not going to worry about, but it's just the features that are found in stars, okay, have wavelengths at their expected values, right, in terms of how atoms emit and absorb light, which we understand. And then we find a galaxy that has a very similar spectrum to this blue one, but everything has been shifted to the right, to longer wavelengths by a factor of 1 plus this factor Z. That's how we infer this factor redshift. So the length of that arrow, you see, that feature there has been shifted from that wavelength around 400 nanometers or 0.4 microns, the blue end of the visible spectrum, all the way over here into the red end of the spectrum of light. And then, of course, this spectrum here has been shifted by that same factor. Okay, you see, it's the same spectrum, but just shifted to longer wavelengths. And then down here, we have another pair of galaxies, and these are at a redshift of 1.5. And of course, this redshift is 0.5. The scale factor here that scales wavelengths observed to wavelengths emitted is now a factor of 1.5. And so it's going from 1.4 microns all the way to 1 micron. So we're going from the blue end of the visible spectrum for this feature here, all the way into the infrared. So this is the spectrum we observe. The one was emitted is this one, okay? And the ratio of wavelengths is this factor, this scale factor of 1 plus the redshift. Let's see. So 1 plus this redshift is often referred to as the expansion or stretch factor, because the universe is expanding over time. And as it does so, the light traveling through it is effectively stretched in wavelength. Think of it that way, in some sense. Oops. And so this redshift parameter, redshift 0 means the object is nearby in space and time. That's a very local universe. Whereas Z large, like this is significant, this would be large, okay? And of course, we'll see other redshifts that are much larger than that. Means light that we observe here and now left long ago, and the object is now very far away. So how does this work? Well, this is a series of little cartoon here. So imagine a supernova went off a very long time ago in this galaxy over here. And this is the Milky Way galaxy over here on the right. All right, so some time ago, very long time ago, a supernova went off in this galaxy. At that time, that galaxy and the Milky Way were about 6 billion light years away from each other in distance. Now, so this exploding star is going out into space in all directions, and this yellow line here represents the sort of the front of the information carried by that explosion, moving at the speed of light. All right. and is approaching the Milky Way, but it hasn't arrived yet. And more time goes by. It still hasn't arrived yet. But look what's happened. Our distance between us has changed over time such that when it does arrive, here and now, okay, we're now a factor of 3 further away from each other than we originally were there and then. So when we're observing this galaxy with that exploding star going off, we see that galaxy's wavelength shifted by a factor of 2 plus 1, 3 to longer wavelengths. The redshift of this galaxy, we say, is 2. And so this shows time moving in this direction and space moving in that direction, and space is expanding. And again, another way to think about it is just the contents that are getting further apart. So the distance now, it turns out, is equal to distance then by this same stretch factor that we measure. Again, we measure this redshift from the spectrum of the object here and now. That's where the astronomer is, in this galaxy, observing out there something right now. And the distance now has been increased by a factor of 1 plus this redshift that is measured from the spectrum, where all the wavelengths of light have been stretched to longer values. And 1 plus that times the distance then gives us the distance now. So we've gone from, when this supernova went off, this exploding star went off, we were about 6 billion light years, 5.7 billion light years apart. We're now presently, when that light has arrived here, and just now noticed this supernova went off in that galaxy, we're now separated by 17 billion light years. This G stands for giga, all right, just going forward. So this is billions of light years, billions of light years. The light travel time here in this example is about 10.5 billion years. So it took light 10.5 billion years from the time it went off over here until it arrived over here. Another way to think about this is, imagine you're running a race. And while you're running, and they say, go. And you all take off the starting line. But while you're running the race, someone keeps moving the finish line. You eventually cross, okay, but it might take a little longer to get across the finish line. There's a little animation of all that. So this is the Milky Way galaxy. This is the other galaxy. Something happened over there. Maybe the big starburst of, I think, give an example. Initial big starburst of star formation within that galaxy took place some 13 billion years ago. And this little yellow arrow here is carrying that information in the form of light, moving at the speed of light. So it arrives here. And now, this is the age of the universe ticking by. This example here could have the universe age, present age, to be 14 billion years. So the age of the universe at the time of the emission of light we see now is 1 billion years. And the distance at emission, so again, to start at the animation, the distance then was about 4 billion years, light years. Okay, again, we'll use a G to stand for billion. The age of the universe, the reception of light, well, that's 14 billion years for this example given here. The distance of the galaxy at reception of the light carrying the information about this big initial starburst of star formation in that galaxy over there is now 28 billion light years. Light, the time that light took to travel from there and then to here and now. Sometimes this is called the light travel time. Sometimes it's referred to as the look back time. How far back in the past are we seeing this galaxy now as we observe it? This is 13 billion years. The observed redshift of the galaxy, we're on this galaxy over here. We measure the spectrum of the light of the big burst of star formation to be a redshift of 6 based upon the shift of the spectral features to longer wavelengths by a factor of 7, 1 plus the redshift. That also corresponds to the difference between, or the ratio between the distance then and the distance now, same stretch factor of 1 plus the redshift. So we start off being 4 billion light years away when the universe was 1 billion years old, and then something happened, boom, that information arrived 13 billion years later, the Milky Way, and that galaxy is now 28 billion light years away. All that has ever been within our space-time horizon lies within a present distance of about 47 billion light years. So here's the Virgo supercluster is a supercluster that our Milky Way galaxy belongs to. A supercluster is nothing more than a collection of many clusters of galaxies, thus a supercluster, and it's the biggest coherent structure we have in our universe are called superclusters. And that's at the center of this diagram by design. And this boundary out here is 46 or so, almost 47 billion light years away from us in all directions. The diameter of which, of course, corresponds to about 93 billion light years. But our universe must be far, far larger in size. I mean, there's no reason why our universe should stop at this cosmic horizon, any more so than why the Earth stops at the horizon where a ship goes, goes over the edge, right? Right. And we can even estimate what that can be because we measure, I won't go into a lot of detail about this, or any detail about this, but we can measure something about the spatial curvature of space from the signature, observational signature of this background of radiation left over from the Big Bang, and based upon how close that is to being zero curvature, we can only pin it down to some fraction amount of it within zero curvature. But if to the extent that it has something different than that, we can estimate then what the physical size of our universe in total must be. But that's just an estimate. All right, now I'm going to put everything together. This is a little busy, but bear with me. We've talked about two different distances: distance now, distance then. Distance then is the distance between us, I mean, you and I on this galaxy, okay? But the Milky Way galaxy, distance between the Milky Way galaxy and some other galaxy when something happened over there, okay? When the light that we see now was first emitted, that's the distance then. We mentioned the distance now. That's how far away the galaxy is now after the universe has expanded and someone's moved the goalposts or the finish line, right? And we talked about the light travel time. So here we are on the vertical axis here, we have a distance measured even in space or in time. In space, these are giga light years, billions of light years, so 5 billion light years, 10 billion light years, 15, 20, and so on. Or distances in time, this look back time or light travel time, how long it took light to travel from there and then that event to here and now that we observe it. All right, so let's start with the look back time. Over here at low redshifts, this is our local universe. Okay, the redshifts are very small. The expansion of the universe is very small. Locally, galaxies are not distributed by any stretch of the imagination homogeneously. Their gravity has compacted them together. And of course, you're not expanding, right? Because you're held together by electrical forces, and our solar system's not expanding because it's held together by gravitational forces. And so our local universe consists of clusters of galaxies that aren't undergoing expansion, all right? And so that's over here in the far left-hand corner over here. And as we measure galaxies of greater and greater redshift from 0.01, which is about the limit that we can actually measure a galaxy participating in the overall cosmological expansion of our universe, has a value of maybe about 1% in redshift, right? And we proceed to the right, okay, we measure larger redshifts. I mean, let's follow the green line here, the look back time or the light travel time. And you can see that as we look further out into space, at greater and greater redshifts, we're looking further back in time, such that eventually we're seeing all the way back to the present age of the universe. That green line asymptotes to matching the present age of the universe at very large redshift. All right. distance then. This one's kind of interesting. This is the red one. Again, distance now, distance then, and this look back time all pile up over here to this virtually the same value, as we'll mention this in a minute. Okay, but then as we reach redshifts of 0.1 to 0.2, these begin to separate from each other, because on those, well, as the light travel time begins an appreciable fraction of the present age of the universe, the distances now and then begin to separate, and the quantity of the speed of light times the look-back time, or the light travel time, ceases to be a useful indicator of distance. I mean, this green line has to asymptote to the present age of the universe at infinite redshift in the very early universe, long ago in time. Let's go to the red one. That's the distance then. So initially it increases just as you expect, right? If it has a higher redshift, it means the galaxy is further away. This is what Hubble found in 1930. But this is the distance the galaxy was from Milky Way, or the local group of galaxies, at that time, when the light that we see now left that galaxy. And that goes up, it reaches a maximum. The maximum is about, at a value of redshift of about 1.6, about corresponding to about 10 billion years ago in time. That's this value here, that maximum. So a galaxy at redshift of 1.6, we're seeing it back when it was, as it was 10 billion years ago. And that is the most distant object that we can see in terms of its distance being the distance then. Because after that, at greater redshifts, that value, that distance then starts going down. And if you just give that a little bit of thought, it's because we live in an expanding universe. If we look far enough out into space, we're looking far enough back into time that everything was closer together, a lot closer together. And that's what's happening here. Finally, we have distance now. That's the blue curve. Okay, and it's simply just the red curve multiplied by this 1 plus the redshift factor. And so we go from small values over here of order fraction of a billion light years or a billion light years over here to up to this maximum limit here, as I mentioned on the previous slide, of about 46 billion light years. This galaxy, this is an image from the James Webb Space Telescope, and we got to get Mike to focus the camera here, because this one's a little bit out of focus, but this is a big field here of distant galaxies taken by the James Webb Space Telescope, and they found a galaxy in here has a redshift of about 14.3, which is presently, as of today, as far as I know, as far as anything published, holds the present day record for the most distant galaxy, having the highest redshift. Oh, but wait a minute. Is it the most distant galaxy? Or is it? Because at that redshift, looking so far back into time, the universe was all the constants of the universe were much closer together. The age of the universe at the time this light left this galaxy, which is not very big, but there's only a few tens of thousands of light years in size. This is a small galaxy. The time this light that we see now left that galaxy, the age of the universe is only about 290 million years. It took light 13.5 billion years to get here from there, given the expansion of the universe in time. So this distance now is 34 billion light years, which does make it a record holder in distance of a galaxy. We'll probably find a few more that are at higher redshift, looking further back into the past. and have a distance now that's further away. But the distance then is only 2 billion light years, which isn't all that far away. I mean, the nearest quasars are about that far away, about 2 billion light years away. 3C273, the nearest luminous quasar. And that's only, I mean, 2 billion light years is only, it's just beyond our local neighborhood of superclusters of galaxies. And so this distance then is equivalent to that of a galaxy with a redshift of only 0.2 in the local universe, or relatively local universe, with only a look-back time of about 2 billion years. So depending on what distance you're talking about, this one's not all that far away, or at least it wasn't all that far away when the light that we see now left there and then. So we're almost done, but I just wanted to warn you, we're going to look at some expanding space-time. This is a space-time diagram for our expanding universe, which is at present age of 13.8 billion years. I'm going to fill in the pieces here. So at the center here, that actually says BB, stands for Big Bang. Imagine looking down on the North Pole of the Earth. That's like this. And you know how globes have lines of latitude, right? Going down this way towards the equator. They have lines of longitude go around like this. So the same thing. These have lines of latitude, which are measured in this direction. We have lines of longitude going around this way. So the lines of latitude in purple, which maybe you have a difficult time seeing with this. Well, you see some over here are purple, okay? But they're these ones that are going around like this, okay? These lines of constant latitude tick off 1 billion years of cosmic time. So this would be, I don't know, a few billion years, and this maybe it's 5 billion, 6, 7, 8, 9, and so on, up to 13.8 billion years, as we'll see in a moment. So as you move away from the pole here, which is the Big Bang, a moment of time, okay? In any direction, you're increasing the age of the universe. All right? And then lines of longitude, which are going around like this, okay, they're being measured along that direction, okay? Those are, shown in blue, are separated by 1 billion light years in distance now. So, as we'll see in a moment, this is our location right now. And along this curve, each one of these marks tick off 1 billion light years. But as we move further this way, further back in time, these separations get narrower and narrower and narrower. That's the distance then. Gets smaller and smaller and smaller by a factor of 1 plus the redshift. All right, let's fill in the pieces here. Okay, we'll come back to that in a moment. Let's go. There we go. Get a little bit of delay. This is our Milky Way galaxy right now. The age of the universe is 13.8 billion years. There's a galaxy. Something happened in that galaxy, or I don't know. We just found it on a survey in the sky, and we observed to have a redshift of, we'll see in a moment, 6. And that galaxy on this diagram here of space-time sits right over here. Then, the age then was 0.9 billion years. This is the age now. So where was the Milky Way? Well, it wasn't there. It was over here. Milky Way was here when the light of that object left that galaxy and eventually rise over here. And of course, what happens in between? Oh, all right, sorry. The distance then was 4 billion light years. What happened in between, of course, was the universe expanded. It went that way, we went that way. And so we're not 4 billion light years away from each other anymore. Oh, here's the galaxy today. We don't see that galaxy over there. I mean, we never observe the galaxy today. It's something that we observed it so far back in our past. It's stuck in our, in the history of the universe. We will never observe this galaxy under these conditions here at this age. The orange line here represents the distance. Okay, remember distance is measured along constant longitude here. And this is 28 billion light years. This initial distance was 4 billion light years. This red path is the line that light takes to go from this galaxy there and then to our galaxy here and now in the space-time diagram. It took about 12.9 billion years. And when that light of that galaxy emitted back then arrives at our location now, we measure a redshift of z of 6. That means the spectrum has been shifted by a factor of 7. The universe has grown by a factor of 7, 1 plus the redshift. This distance, in ratio of this distance, is that factor of 7. And distance, this is the distance in time the light took to go from there and then to here and now on the space-time diagram. And finally, the other thing to note is if we happen to observe a supernova going off, an exploding star going off in this very distant, well, high redshift galaxy, and if the characteristic time scale for the brightness of that exploding star to reach the maximum luminosity is, let's say it's 10 days in the local universe. Like if that star exploded in our local universe, we'd see that time maybe takes 10 days to go from initial light to the maximum light. This is an example. And likewise, in its frame of reference, there and then, that time scale is about 10 days. But when we observe that brightening of the star, this exploding star, here and now, it doesn't take 10 days to reach that maximum in luminosity. It takes, you guessed it, 10 times 1 plus the redshift, 7. 70 days to reach maximum in our frame of reference here and now. This is the same space, but now allowing you to see it's kind of an additional dimension. Everything was flattened before. These are the same curves. So space-time in an expanding universe is curved. Even if our space that we live in is geometrically flat, or we know it's something which is asymptotically approaching something flat, but space-time is curved in an expanding universe. So distances in space are no longer unique. We've got a distance now, we have distance then. Which one are we talking about? In the local universe, it doesn't matter. Not much happened if the galaxy is only, I don't know, 50 million light years away. Not much happens in the expansion of the universe in 50 million years. So there's almost no difference between distance now and distance then. And if you multiply that look-back time by the speed of light and call that a distance, well, it's almost the same value as both those distances. But certainly, once you get out to significant redshifts, we're looking far enough back into space that the universe has dramatically changed its scale over time. Certainly, this measure here of distance becomes meaningless. And we shouldn't use it. I mean, if you ever hear that a galaxy is a distant galaxy discovered by astronomers is 13 billion light years away, right? You can just disregard that because they're quoting, for some reason, they decided to quote to you the speed of light times that look-back time. What they're actually telling you is the light that we're observing today in our galaxy here today took 13 billion years to get here. The light travel time, that's what they're quoting to you. And the distance and the two other distances, there's something very different. Things that are actually measuring spatial distances are two other numbers that have nothing to do with that meaningless measure of distance. Okay, so we should think of the look-back time or light travel time as a distance in time, not in space. And so we shouldn't be mixing the two up. ever since the Hubble Deep Field in the 1990s and some of the subsequent galaxy surveys, at high redshift, came in the 2000s. There's a lot of press on the discovery of the next highest, redshift quasar or redshift galaxy or whatever. And on almost every case, they were quoting a distance, which is turning a look-back time or a light travel time into a distance. And again, for these kinds of distances and redshifts, that was a meaningless number. But it seems like we've gotten away from that in recent years, which is a good thing. Thank you.